It's great that we are now properly tagging our packets, but at some point the device in question, let's say our fabric interconnects, need to know what exactly we're going to do with those packets of various tags. And what we're going to do primarily is use the concept of queuing and scheduling in order to make sure that the higher priority packets make it out, or more specifically in our UCS environment, that we've got the ability to deploy bandwidth reservations to certain traffic classes. If we want, for example, live migration in order to get a certain amount of bandwidth, well, then we need to make sure that happens. And queuing and scheduling is how exactly we go about doing that. So let's dive in and take a look at this. We started this conversation in the last video, but we have this idea that we're going to have a lot of traffic coming into a switch, and potentially the amount of traffic we need to send out a single interface, we've got too much of it. We can't just send it all at once. It would be a lovely reality if we could say, well, as soon as this packet comes in, it gets sent out, and then this packet comes in and it gets sent out, but it takes time. It takes time in order to send a packet, and yes, we are slowing our time intervals down to the millisecond and possibly even microsecond level, but it is what it is. And so what we end up with is the idea that we have a lot of packets that are lined up, and this line is called a queue. We queue up these packets, and they are waiting their turn, essentially, to be sent out the hardware line. And so this packet is going to get sent first, and once that one's done transmitting, we have another packet in line, and the risk here is that this packet, maybe the fourth packet back, is a very important packet. And this important packet needs to go as soon as possible, and yet it has to wait its turn behind these three other packets that need to get sent. And wouldn't you know it, those three packets are very large, and so they're going to take a long time to send. So the solution for this is to not just have a single queue, but rather have multiple queues. We need a plural amount of queues so we can choose which of our queues to send at a given time. In order to see this best illustrated, let's take a look at an example. Let's consider the idea of us all at an amusement park together, waiting to get onto a roller coaster. These roller coasters are a whole lot of fun, or they're a whole lot of terrifying, depending on your perspective. But either way, we are lined up behind a lot of people. So there's a lot of people in line here. I don't know about you, but I've been to amusement parks where I've had to wait literally over an hour, sometimes even 2 hours, just to get onto the ride. And of course, the ride lasts 10 seconds, and hopefully it's worth it. But either way, here we are back here in the back of the queue. You and I have to wait for all of these people in front of us to get to go, and by all rights, this is a very fair way of doing it. Presumably, this person up here arrived first, and then this person arrived second, and then third and fourth, and however many people are in front of us, and then we arrived next, and so we just get into line. Very fair way of doing this. But here's the problem. Let's say somebody shows up back here, and maybe a couple of people, and these would be considered very important persons, otherwise known as VIPs. Maybe it's the son and daughter of the owner of the amusement park, or maybe it's some important investor who wants to check out the newest roller coaster, and so they're getting in line, except again, they matter a whole lot more to this amusement park than any of the people who are in front of them, including you and me, by the way. Now this idea of fairness starts to take a turn, because even though it's perfectly fair that they arrived last and they should have to wait an hour in line like the rest of us, we know that the reality is that those individuals should get to go ahead of everyone else who's waited in line. And so the solution to this idea is to create a second queue. These individuals, the VIPs, are going to get into a separate queue, so they're no longer down here with the rest of us. Now, when the person who's in charge of the roller coaster, this staff worker right here, looks for the next person to put on the roller coaster, they're going to see that there are people in this line and there are people in the VIP queue. And so they can choose to allow the VIPs to get on the roller coaster first. Now, this methodology, by the way, is used in a lot of theme parks today. To be honest, it's less about a VIP showing up and more about the idea that we allow customers to purchase something along the lines of what many places might call a fast pass. It allows patrons to either pay more money up front to gain access to these fast pass lines, or possibly put in a reservation. And by putting in a reservation for maybe like 2 p.m., I'll come back to this ride, that enables them to get into the fast pass queue. And so this is a great way for managing traffic at an amusement park, and guess what? It applies really well to our networking devices in our networks. Now, as far as general QoS concepts are concerned, I do want to point one thing out, and that is, in this scenario, are we able to allow more people to ride this roller coaster? And the answer is no. We are not able to fit more people onto the roller coaster by having multiple queues. If we're able to service 3,000 people a day, well, we can have 1 queue, 2 queues, 10 queues, doesn't matter. We're still only capable of servicing 3,000 people a day. And that's also true with network switches. So having all these different queues can allow us to do some other QoS manipulations that are outside the scope of the DCCOR course, but at the end of the day, we're not able to service any more packets this way. In many cases, QoS is really just a mechanism that decides which packets to drop, rather than making it so we don't have to drop any packets. And of course, at that point, we would want to drop the lowest priority packet, whichever priority level that might be. So let's get back to our routers and switches. A lot of times when we have an interface like we drew above, we're going to split this up into a lot of different queues. Now, some devices will support 4 queues, some devices will support 8 queues. Routers can support up to 256 queues in many cases. However, from a Nexus perspective, and when we say Nexus, by the way, we also mean fabric interconnects, they're going to be divided up into 4 or 8 queue hardware models. In our fabric interconnects, we can expect to see 8 queues. These queues are the traffic classes we talked about in the last video. So we talked about platinum and gold and silver and on down. And so all of these different queues line up and we end up having 8 different classes that get assigned to these 8 different queues. Furthermore, the system allows us to place bandwidth reservations on a per queue basis. So I can say platinum, for example, we get 10% of the bandwidth. And for gold, we get 20% of the bandwidth or what have you. And these bandwidth reservations are going to ensure that some amount of traffic gets through even in times of congestion. Now, furthermore, on Nexus devices, we have this concept of priority queues. We can place a particular traffic class into a priority status, and that makes it so any packet that arrives in that queue will get sent out the moment it arrives. It's automatically put to the front of the queue, kind of like our example over here with the VIPs. Now, all this configuration is great, but at some point we actually have to implement it. And that process is the responsibility of the scheduler. The scheduler is going to enforce the policy that we just configured. It's going to service packets out some queue, let's say the platinum queue. It's going to grab so many packets out there, and then grab so many packets from gold and silver, and maybe some that are lined up in bronze and such. It's going to ensure that the amount of packets that we're pulling are tracking against the bandwidth reservation. Furthermore, if, for example, the interface is bored, maybe we don't have a whole lot of packets right now, at that point, we'll allow traffic to exceed its own bandwidth reservation. For example, if we're just sending a lot of gold traffic, we might allow it to consume 80 or 90% of the bandwidth link as long as none of the other queues are filled. And so we can always use more bandwidth than what we've been given. However, in times of congestion, this reservation is also going to turn into a limit because we might have a whole lot of platinum traffic, but we've only given it 10% of the network bandwidth. And because we're congested, we're going to have to end up dropping a whole lot of platinum packets. So as we review this, queuing is how we buffer packets that are stacking up. Remember, we can't just send a packet immediately. There's a real amount of time that it takes to send a packet. And yes, we do have to shrink our time frames down to really, really small values. But again, that is just the reality. We're going to have to line these packets up and have them take turns going out the output interface. Now, multiple queues are going to give us control over which packets we can send. So we saw that with the example at the amusement park, and then we turned around and saw it on a routing and a switching device. So we've got 8 different queues, and we can service whichever one of those queues that we want, ensuring that we have access to some of the packets that we've given bandwidth reservations to. Now, the way we figure that out, by the way, remember, that's the UCS traffic class concept. And so if, for example, the platinum class is still mapped to COS of 5, which is the default, then when a packet arrives on an interface and it's tagged with 5, we know that that goes into the platinum queue. And lastly, it's the scheduler's job to figure out where exactly or when exactly we're sending a particular queue. So we want to make sure that we're abiding by the bandwidth reservations. In other words, hey, you're guaranteed to get maybe 10 or 20% of the bandwidth, but in times of congestion, that is also going to turn into a limit. And the scheduler is going to make sure that all of the queues get access to the amount of bandwidth that we've given it. I hope this has been informative for you, and I'd like to thank you for viewing.